Here you have two categories, compact and non-compact groups. Let's look at examples of each category. Supposing I have G is equal to 1, 2, 3, 4, and the operation is multiplication modulo 7, sorry 5, multiplication modulo 5. What is this operation meaning? If I multiply 3 with 3, I will get 9. But 9 is not an element of this set. But when I say 9 modulo 5, I must divide 9 by 5 and take the remainder, whatever is the remainder. It will not divide it, but you will have a remainder, right? That remainder is what is the answer. So 9 means what should that element be? 4. 4 into 4 is 16. What is that element? 1, because 16 minus 15 is 1. So that is, so this is an example of which category? Finite group, because order of the group is 4. So what is the multiplication table of this? 1, 2, 3, 4, 1, 2, 3, 4, and this is multiplication modulo 5. 1 is the identity, so this is same, this is same. And what is 2 into 2? 4. There is no problem because it is less than 5. 2 into 3? 1. 2 into 4 is 3. 3 into 2? 3 into 3? 3 into 4? 2. Correct? This is 4. 4 into 2 is 3. 4 into 3 is 2. 4 into 4 is 1. Is this a cyclic group? Is this a cyclic group? We have actually two conditions for a 4 element set to be a group. One is cyclic group, the other is the group which we just discussed with 3 generators. Each one is its own inverse. Correct? Is it like that? 2, 2 is not identity. So this has to be cyclic. These are the only two conditions. Up to 3 element group, only one condition. For 4 element group, there are 2 conditions. And this is a cyclic group. It is not self inverse, so it has to be cyclic. So 2 is a generator. 2 square is 4. 2 cube is 3, 2 power 4 is 1. So it is a cyclic group. Generator is 2 and order of 2 is equal to 4, which is equal to the order of the group. Let us consider G as set of all integers. And the binary composition law is usual addition. Is this a group? Is this group an abelian group? You don't have to check, because I told you every group less than 6 is an abelian group. So is this a group? How do we check whether it's a group? You have to go back and satisfy all the axioms. Here we could write multiplication table, but what is the order of this group if it's a group? Infinity. But it's a discrete group. because between 1 and 2 there are no elements. There are infinitely many elements, but there are denumerable or countable. So it is a discrete group, but it is an infinite group. What is the identity here? 0 is the identity. Okay? So in this group, identity is usual 0. Now for every m in Z, we have m inverse. What is m inverse? What is m inverse? Minus m. Is it an abelian group? Huh? Is it an abelian or non-abelian? Why? Still it is an abelian group. You take any negative number, add a positive number, or positive number, add a negative number, you will get the same, right? So this is an abelian group. So Z plus is an abelian group. Z plus is an abelian group. This is an example for discrete group of infinite order. Order of this group is infinity. Now take another example, that I have a plane, xy plane, and I have a vector denoted as r, and I make a rotation of the coordinate system. Okay? So I will make a rotation of the coordinate system. This is my x prime, this is my y prime, by an angle theta, and ask a question: what will happen to the coordinates of this vector in the new frame? So you can say that the rotation is affected by a rotation matrix. Okay, so you will have a matrix called r of theta, which is equal to cos theta sin theta minus sin theta cos theta. So now if I consider G as set of all such matrices, cos theta sin theta minus sin theta cos theta, such that 0 less than or equal to theta less than 2 pi, 0 less than or equal. How many such matrices are there? Infinitely many matrices are there. What is the composition here? Matrix multiplication. Now you can see that every element is a group element. I have infinitely many elements. It's not discrete, because theta varies continuously. You take theta as 0.1, 0.2, in between there are infinitely many thetas, and for every theta you have a matrix here. So it's a continuous variation of a parameter. So this forms a group, which means you take r of theta and r of phi, multiply them, you will get r of theta plus phi. Now theta plus phi will be another angle in this set. So what happens? You have closure, associativity, identity. What is identity? Theta equal to 0. Don't do anything, no rotation, is the identity. That is 1 0 0 1, usual identity matrix in 2 by 2 matrices. Inverse, for every matrix it transposes its inverse, because this is an orthogonal matrix. So for every matrix it transposes its inverse. So you have all the group parameters, and you can also show, I mean it's trivial to show, otherwise we can do it in tutorials, that this is also an abelian group. because r of theta into r of phi will be same as r of phi into r of theta. So this is an abelian group. Now, so here group element depends on a real parameter. In this case theta. Now, if the parameter theta varies in some space, right, in this case 0 to 2 pi, okay. So theta belongs to what is called 0 to 2 pi. So this is closed interval 0 to 2 pi. This is called parameter space. Okay, this is called parameter space. Now, if the parameter space is closed, if the parameter space is closed and bounded, we call the group a compact continuous group. A compact continuous group. The parameter is only varying in a closed interval. It's continuously varying, but there is a bounded, it cannot go beyond 2 pi. It cannot go below 0. So 0 to 2 pi is a closed interval in the entire real line. So like that you have a compact interval, then the group is called a compact continuous group. This group is called SO2, special orthogonal. Special orthogonal group. Okay, when we come to third day of this course, we will discuss about continuous groups in detail. So this is called SO2, that is rotations on a plane, proper rotations. Special because these are proper rotations. Proper rotations will have a property that the determinant of the matrix is equal to 1. If you take an orthogonal matrix, its determinant can be +1 or -1. So we are not considering all those matrices whose determinant is -1. If you consider all those matrices whose determinant is +1, we get what is called SO2, and SO2 is a compact continuous group which is abelian, an abelian group. Yeah. Huh? 2 is, yeah, so you can 2 is not its dimension. This 2 only says that the rotations are in 2-dimensional space. Okay. We also have the concept of dimension of this group. Dimension of the group is equal to the number of parameters. In this case, of this group is 1, because there is only one parameter, theta. Okay. So it is good you mentioned, so let me write it. So dimension of SO2 is equal to 1, which is defined as number of independent parameters. Now maybe let me just ask you, some of you may recall, if you take rotations in 3 dimensions space, 3-dimensional space, Okay, what is the dimension of that? That is called SO3. Huh? How many parameters are there in 3-dimensional space? 3 parameters are there. What are those parameters? Huh? Euler angles. Yes, from classical mechanics you might recall that Eulerian angles will determine any arbitrary rotation in 3-dimensional space. So 3 Eulerian angles will become independent parameters in rotations on 3-dimensional space. So they will become the parameters. So dimension of SO3 is 3. So I have given an example for finite group, infinite group, compact continuous group. Let's consider an example. So you have, let's say, a translation group. Okay, translation group. Suppose, let's say that I have translation group. So T on any f of x, any function will affect this. T on any function will make this f of x plus a. Okay, just one-dimensional translation along x-axis. Okay, now T depends on a. Now I can define group as set of all such translations such that a belongs to minus infinity to infinity. Now this one upon translation, so what is the meaning of group operation? If T of A and T of B is actually T of A plus B. Correct? So what is the parameter? Parameter is A. Parameter is A. What is the parameter space? Parameter space is minus infinity to infinity. That is the entire real line. Entire real line. Is this closed? There is no bound, so it is not a compact group. This is an example of